Hello and greetings to you all. To our dear viewers, we are very pleased and happy to be here with you today, along with our dear students. Today's program is about support vector machines, which is one of the important topics in machine learning, data mining, and related fields. It's one of the most powerful algorithms that's used both in the job market and in your coursework. So, what topics are we going to cover today? I'll start with an introduction to support vector machines, what they are, which area they belong to, and I'll give you an intuitive understanding of support vector machines. A definition in mathematics. It's about hyperplanes, which you're already familiar with. I explained it fully in previous sessions. I'll also give some specific explanations about hyperplanes, and then we'll get into the problem itself. How do we model this problem? What is the structure of our model? I'll introduce a primal problem and an initial problem. Then, thanks to that, I'll construct the dual problem and explain the relationship between them, and you'll see what happens in the primal and dual problems. All right. The first part, which is very important and I also mentioned in previous sessions, is the discussion for you about various different approaches. It's about machine learning. One of the approaches, which I explained before, is supervised learning. The necessary explanations about this were given in previous sessions, and you all know that supervised learning is divided into two main categories: classification and regression. Classification. Well, we translate it as categorization or classification, and regression is also called regression. Among the most well-known classification algorithms, I can mention neural networks, KNN, decision trees, Bayesian, and logistic regression. But one of the most, and the most powerful and popular classification method is the support vector machine, which today I want to talk about. I'll give you the necessary explanations about support vector machines in the context of classification, which will be very helpful. Do you know what this concept is? It was explained in previous sessions as well, but let me explain it again with a simple example. For example, let's consider a bank, and let's say there's an employee at the bank. Their job is to review the background and history of a customer, to see whether this person should be granted a loan or not, whether the loan is approved for this person or not, or to predict whether to give them a loan or not. There's a very well-known classification method, and SVM is, in any case, one of the branches of this classification method. Here's another simple example in the medical field. In medicine, let's say someone has a set of medical data. Based on that, they want to determine whether this person has cancer or not. If they do have cancer, which methods and treatment approaches to use. For example, if there are 3 treatment options, which one should be chosen based on age, for instance? This is one of the classification problems, and one of our powerful tools is SVM. In fact, it's very important here, this particular method, because it can effectively work with very little available data, meaning the data is specifically labeled and subsequently used for training purposes. That is to say, training data, it can still adequately do the job. And you know that, for example, in the critical field of cancer research, meticulously labeling this kind of data will undoubtedly cost you a significant amount. It will also take a lot of time, and that's why it can do the job with just a small amount of training data. So, please pay attention here. Today, as I'm speaking with you, I'm focusing on support vector machines, or SVMs. I want to speak to you and tell you that this is the part of the meeting that we will talk about, but in the regression basin, as you are in isolation, when I give you an example, a very simple example in the basin. It's about real estate. For example, suppose you have the size of a house, the location where the house is situated, and let me add, we've mentioned the neighborhood, we've mentioned the age of the house, and we have other information, other features as well. On the other hand, we want to predict the price of the house. So your prediction here, as you can see, is a prediction that falls within the real number space. Now, since the price here is positive, it's actually in the positive real number space. That's what happens. In this situation, we use regression. And one of the very important methods, which I also explained. In the next sessions, we'll cover the support vector regression method, which I've also explained a bit about. All right, let's do a quick review. I'm going to talk to one of our dear friends here and ask if we want to explain support vector machine, which category does it belong to? Give us a brief explanation in the field of machine learning.
Support vector machine, as the professor mentioned, falls under the classification or discrimination category. In supervised learning, it's like this. We have a set of data with assigned labels. We use this data to train our model, and then we ask it questions. The answers should fall into one of the categories we've defined for classification, which the support vector machine handles. Is this one of the modern types? Yes.
Thank you very much. You pointed that out correctly. Let's move on. Next section. Well, this diagram is very illustrative. On the left side, you can see two sets of data. One set of our data is labeled in blue, and another set is labeled in red. Here, you can see them represented with red and blue colors. So, what is our main goal in support vector machine? It to be able to separate these two sets of data that we have here. So, it's very simple. Our main goal is to separate them. Just to clarify, these two sets of data in this diagram. As you can see, and it's quite clear, our data is completely linearly separable. That is, with this hyperplane here and this hyperplane over here, as you can see. You were able to do this quite easily. Later on, you'll see that this distance you observe here up to here is our margin, which I will define for you. I'll explain. But in this diagram that you see here, this shape is not linearly separable. This is about nonlinear data separability, which you'll see in the upcoming sessions. When I talk about the kernel domain, I map this space to another space. I will do that, and you'll see that in that case, they become linearly separable. But right now, when you look at the left image and the right image, as you can see that here they are linearly separable. Today, in this session I'm talking about, my assumption is that my data, what are they? Yes, they are linearly separable. We can separate them linearly, so with this assumption, I'll start my work. Well, before we get into the discussion of margin and other topics, in my previous sessions I introduced a number of papers and articles about support vector machines, both my own work and that of others. But one of the most important articles, which I strongly recommend my dear friends to definitely read, is this one. It's about support vector networks, which is the work of Ms. Cortez and Mr. Vapnik. We've mentioned Vapnik in previous sessions. I've also referred to him before as the father and the originator of support vector networks. What should we do? We should definitely count it in, and this article has done an excellent job. This article was published in 1995 in the Journal of Machine Learning, and interestingly, it focused on the nonlinear domain and worked more on nonlinear problems. When they mastered this field, and in their previous articles, which you can see here, in 1992, in 1982, and in 1994. With various people, as you can see, they worked on this same topic of support vector machines. Training algorithm for optimal margin classifiers, estimation of dependencies based on empirical data. And another article that we see here, my suggestion is that you can also take a look at other related articles that are available. In this regard, related to this session, is there anything that could help you? All right, now we want to get into some intuition and try to understand. Let's see what Support Vector Machine is all about. So the first point I want to explain today is the concept of margin or boundary, which is what I'm explaining about Support Vector Machine as well. Later, you'll see that I'll bring up the topic of hard margin when the data is separable. But first, let's see what margin actually is. Here, you can see two types of data, squares and circles. We want to separate the squares and circles from each other using a certain method. Well, as you already know, and as is mentioned in the following slides, there can be a significant number of hyperplanes that can do this job. But the important feature that Mr. Vapnik had, and the work he did, was as follows. If you pay attention, if you consider this hyperplane, there are two other hyperplanes as well. If we draw these parallel to this, the distance you see from here to here is called the margin in a support vector machine. What you're aiming for is to maximize this margin. It's pretty clear. Right now, you can see a margin here, and there's also a margin here. Which margin is it? Razai, is it better? Mostadar, are you there? Yes, just as you are present, just as you mentioned, and as was correctly said, here you are trying to maximize this margin or boundary. Where does this boundary occur? It happens in this distance, and we'll see that this is how it works. And it's also clear that this margin you have is your best answer compared to the other margins. Because if you make a specific move, a particular adjustment, for example, if you move some of your data, your margin will fall apart. But here, does this minimum mean your operational risk is minimized? Here, well, this was the discussion about margin and the hard margin that was mentioned, mathematically speaking. Now I want to get into how we maximize this margin. How is this problem modeled? Please pay attention. I want to maximize the problem in such a way that these data points, which are the red squares here, as you can see, are above this line, and the circles you see, what are they below this line? Should be placed. All right, let's move on. Before I get into the concept, there's a mathematical definition. It's the definition of a hyperplane, which all of you know. I explained this in previous sessions as well. It's very simple. What is the formula for a line? In 2 dimensions, it's in the form w1x1 plus w2x2 plus b equals 0. Now, if we extend this to 3 dimensions, for example, let's assume we have 3 features. wx1 plus wx2 plus wx3 plus b equals 0. So here we had a line, and here we have a hyperplane here, and a hyperplane here. Now, in this dimension, it's written as w1x1 plus w2x2 plus w3x3, and so on. Plus wmxm and plus b equals 0, right? Okay, I want to show this in a simple mathematical notation so that I can later work with it in matrix form. As you know and can see, this is in the form of W transpose times x plus b equals 0. Well, you know that a dot b is in the form of a1b1 plus a2b2 plus anbn. So here, as you know and can see, it's just like that, w1 times x1 plus w2 times x2, and so on. In x as well, here you can see this, so it's in the form of W transpose. This t you see here is the transpose and transpose of x. Plus b equals 0, as you can see. All right, now I want to get into the definition of the example and move things forward. Let's continue. First, let me go over the assumptions so things are clear. As we mentioned here before, we had two types of data. Our topic was classification, specifically for two classes of separable data. As you know, these are on this side. If you consider this margin, these are on this side. I assign a label to these, calling it label 1, and those that fall on the other side of the margin, I label as what? -1. So that's my definition. My output will be 1 and -1. All right, so my problem is set up like this. Let's move on. So how does it work? My features, my inputs, my x_is, are in the r to the power of m space, and my outputs are labeled accordingly. Because it's a classification problem in the form of -1 and 1, right? So my inputs are in r to the power of m, and my outputs, let me tell you, are -1 and 1. How much data do I have? I have n data points. So, to be precise, my data consists of n samples, x1y1, x2y2, x3y3, all the way to x and yn. The yi's belong to the set, meaning they're either -1 or 1, and this is the separating hyperplane in the form of sine of W transpose x plus b. And as for the sine, which is the sine function, we've explained it before, so it's clear how it works. Here's a very good diagram. I want to talk about it. Southwest, please pay close attention. We said let's set this side to a state where our y is equal to 1. Let's set our classifier to 1. And on this side, based on our assumption, let's set our classifier to -1. So what do I want to do with this margin? I want to maximize it. Mr. Nazari, what is the best margin that I can use to maximize this here? The green line. Yes. It's this green line that, parallel to this, as you can see, we have one which is W transpose x plus b equals -1. On this side, we have W transpose x plus b equals 1. And later you will see, and I will talk about it, that this point and this point are the support vector points, because they are on this border. It's like considering two countries where there's a border patrol, and what is it doing? It's separating them, and that's what happens. Of course, please also note this point here. I have used other classifiers as well. As you can see, this classifier is a very unsuitable one because it hasn't been able to separate these correctly. The one that I specifically pointed out here is actually a type of classifier that, let me tell you, is considered to be quite good, and is designed to maximize this margin as much as possible, which, as you can see, is exactly what has happened here in this particular case. Okay, so here my hyperplane became W transpose x plus b equals 0. This other hyperplane, for this side, became W transpose x plus b equals 1. And this side became W transpose x plus b equals negative 1. And you'll notice that when you have a system and a transpose x plus a transpose x plus b equals 0, you can also have it be greater than or equal to 0, which becomes 1/2 space. And you can have it be less than or equal to 0, which becomes another half space. The intersection of these half spaces essentially becomes this hyperplane, and their union becomes what? R in general. Okay, what's the goal? Mr. Nazari, what is the main goal? To maximize this margin that we have, the buffer that we have. Yes. Okay, Mr. Rizai, what are our constraints? What are our limitations? The data that are above this classifier line, we give them the label 1, and those that are below the classifier line, we give them the label -1. Okay. As both of our dear friends correctly pointed out, our main goal is to maximize what? The margin. I'll say it again. Our main goal is to maximize the margin, for which we have already provided the necessary explanations. All right. We had two labels, 1 and -1. I also mentioned this half space that you have here, W transpose xi plus b is greater than or equal to 1. Right here. Correct. And W transpose xi plus b is less than or equal to -1. Let me tell you, it is in this section. Okay. It has become very simple. It is a mathematical model. Now we have to model it. The goal is to maximize this margin. And our constraints are as follows. If yi equals 1, then this relation holds. If yi equals -1, then this 1. Now, if meaning there is an or here, it's either this one, or it's not, or it's the other one. Okay, how can this be written as a mathematical model? I will get into this. All right, so I want to present the modeling, which is also the primal problem. Before I do that, there are a few points that I should mention from a mathematical perspective, which are actually very simple. First question. Consider this line. W transpose x plus b equals 0. What is the distance of this line from the origin? We want to calculate this. The answer to the question is this. The distance of this, well, hyperplane, here it's a line, from the origin is equal to the absolute value of b over the norm of w. It is the magnitude of w. Here we know because we have different types of norms, and it was explained in previous sessions. Here, our discussion is about the norm 2, which we are using. It's the Euclidean norm that we are using. We want to do this. How is that? How can we prove this? It's very simple. As you are aware, w is actually the normal vector or the gradient vector, which we also explained in previous sessions. It is a vector that is perpendicular to this plane, to this line, to this hyperplane. As you are aware, you can see that w is perpendicular to w transpose x. Plus b equals 0, as we can see here. All right, the first thing we'll do is quite simple. We want to find the distance of a point, like x0. We'll take a point like x0 on this line. When you take a point like x0 on this line, or on this hyperplane, so what does it do? It satisfies it. So here you can observe that W transpose x0 plus b will be equal to 0. All right. Well, it's very clear that the vector W, the normal vector, the gradient vector, is perpendicular to this line. So then, k times W will be equal to what? It will be x0. It's very clear, isn't it? You see here that k times this W is equal to what? It's x0. Okay. What is the value of k? It's very clear. I'm going to do this. Isn't kW equal to x0, everyone? And isn't W transpose x0 plus b also equal to 0? So instead of x0, I'll substitute kW. What is k? It's a scalar. So the scalar comes out and it becomes W transpose W. Got it? Please note, W transpose is a 1 by n vector and W is an n by 1 vector. Their product is a 1 by 1 scalar. Okay, so kW transpose W plus b is equal to 0. So what was the goal? Everyone, the goal was to find k. So we move this to the other side, and it becomes negative b divided by W transpose W. As you can see, and as you know from linear algebra, W transpose W is the same as the norm of W. It's the norm 2 of W squared, right? So you have k equals negative b over W transpose W. And what do we substitute for that? We substitute the norm 2 of W squared. Okay, so k takes this form, it takes this form. So from here, at this stage, if we take the norm of both sides, break time equals 0.5s /, therefore, the norm of x0 is equal to the norm of k times W. Well, we know k is a scalar. It can come out of the norm, and its absolute value comes out. This means it's in the form of the absolute value of k times the norm of W. Okay, so this x0, the norm of x0, the magnitude of x0, which is what we have and are looking for, is equal to the absolute value of k times the norm of W. Everyone, what is k? It's negative b over the norm of W squared. We substitute it, take the absolute value, and as you can see here, we get the absolute value of b, since the norm is a positive value. So, as you are aware, this W cancels with one of these W's, and the norm of b over the norm, the absolute value of b over the norm of W. So, if we have W transpose x plus b equals 0, its magnitude becomes the absolute value of b over the norm of W. Now, for example, if this becomes W transpose x plus b equals 1, it's very clear. We write this as W transpose x plus b minus 1 equals 0. So what does its value become? The absolute value of b minus 1 over the norm of W. I should say it is in this manner. Correct. Okay, now let's move on. Since I want to calculate the margin, it's as if I have 3 lines, or rather, 3 hyperplanes. First, I want to find the distance, and as we can see here, we want to see what the distance between 2 parallel lines or hyperplanes is. It's very simple. I have pointed it out here. W transpose plus b becomes the absolute value of b over the norm of W. Here, I also said we move b to the other side, and it becomes W transpose x plus b minus 1 equals 0. And what does its value become? The absolute value of b minus 1 over the norm of W. Okay, and on this side, it was the absolute value of b over the norm of W. So what does this distance become? It becomes this distance.